which is connected to the mechanical engineer. Whenever you go for any kind of component design, then there is a very important thing. Today's design concept is a fail-safe design concept. That means there will be a stipulated life within which the engineers will say that it's not going to fail. And how is it that we can get confirmed that an engineering component will be able to serve the service, it will be able to tolerate the service conditions until the design life. So that is a point which I will try to highlight, that the tool which by virtue of which we can really do these types of things, that is essentially some kind of modeling and simulation technique. So our topic will be like this, that initially we will introduce the subject. That the subject is essentially we will be using for the COMSOL multi-physics platform. And then here several toolboxes are there. One is your mechanics, and within the mechanics you can get several options by virtue of which you can get the plane stress fracture toughness, strain fracture toughness. So in our case, we'll be looking for a plane stress fracture toughness. This is a demonstration. This is a demonstration. I just want to demonstrate that how do we really use to know the failure propensity of any particular component, or to understand the residual life of a particular component, which is very pertinent to any kind of engineering activity. So I will be taking a case study by virtue of which I will make you understand that what is that which is involved in such kind of residual life assessment vis-a-vis the confirmation that your design component will be able to survive until the desired life. So this is as I said, the tool is COMSOL's multi-physics platform. Is a toolbox. Mechanics is a toolbox, and from there, what is our case studies? Normally, if you look at the scenario of the railway casualties, you will find that more than 80% of the railway casualties originate from the track defects. So the track cracking at the tracks and all those things. Now the essentiality of this kind of modeling and simulation is, how do we know the behavior of crack propagation during this particular operation of the railway track? You can understand that in a railway track, some train is moving, and you know that it is acting as a simple supported beam, because the two what is that called, fish plates are there, and the rest of the track is suspended, and then the track load is gradually increasing, and we want to increase the surface speed also. Then the momentum is also increasing. It means that the downward pressure is also increasing. In that case, the loading is like cycling loading. Let me ask, how is it that it is a cycling? So whenever a well is moving, initially its entire load is supported by the fixed plate, the pivot, whatever is there. And then when it goes to the hanging portion, then gradually some stress is generated inside it. And then when it goes to the top, then the bending moment becomes maximum. And in a simple supported beam, you know that will be the case. And in that case, and when it leaves that thing, then there will be a gradual diminishing of the bending moment vis-a-vis the force on the downward force on the track. And then if you find that this is a typical irregular separate variation of stress with time, and then okay, this pattern will continue. Now let us think that what will happen after some time. You don't have any board, no? You don't have any board, no? Yeah. Okay. And then you don't have a smart classroom also. It's not a smart classroom. You cannot write anything. So it's again the conventional screen. The issue is that, so therefore you have to understand what I'm trying to say. That whenever this is a track, the wheel is moving, and here the two pivots are there, and then once it moves in here, then the entire load is supported. Now when it goes in there, there's some bending moment. So the track is moving like this. So the track gets deformed like this. There is an elastic deformation. When that goes on, when the trace then it recoils. So it requires the track recoil. So that's why you will see that the track is flat all the time. So this is how the entire design is made by you, that it will be within the regime of elastic deformation. Now this is a scenario, but somehow or other, how is it cyclic? Because here you see that is a simple, that means that this is a typical half wave of sine wave or cosine wave. And then next, immediately after that, when the central wheel is one wheel is at the center, the other wheel just entered. So naturally, its contour is going to be superimposed on that. So therefore, ultimately, it will be a very zigzag kind of thing. A very irregular curve will be generated. Now again, the same thing is repeated for the other portions of the tracks. The train is moving. So what happens? After some time, the train passes within the region, within a different region. Once the train passes, then there is no train for say 15 minutes, 1 hour, half an hour. That means the bending moment or the load is a flat. Nothing, no load is there. Then again, some train comes. So once that means that this is as a, and this is this, and then again something is there. This is imposed on this thing. So therefore, you get a very, very irregular cement car. Now you must be knowing that any car can be depicted in the form of a sum of sine waves and cosine waves by virtue of a Fourier series. So once you do that kind of thing, then you will see it's a sine wave and cosine wave. So that means your job is done, that it is a cyclic loading. Now the issue is that to solve these things, no tool is there, and also what I'll be showing you, that is also not possible. It is up to you. I leave the matter up to you for the future research, that how can you incorporate the complex situation of the loads, the cart loads on the railway track, such that you can understand a typical case of fitting loading on that. I'll be assuming that it is a simple harmonic type of thing, and then I'll try to say, no, it's not my immediate task. My task is to know how can I model the crack growth, because suppose a crack is there. Now, whenever a crack is there, whenever you generate a crack, what happens? First of all, any kind of thing that I'm talking. So basically some acoustic waves I'm releasing. I'm waiting. I'm raising in my hand. Then some acoustic wave is generated. So acoustic wave emission technique is one non-destructive technique. And then what happens that once the acoustic emission goes there and it comes here, suppose it hits here. And suppose at the engine, front of the engine, I had that kind of thing. And I have a sensor. And then once it comes back, then this is the normal time, 1 cycle time of reflection. If there is any crack, then there will be a scattered reflection. So scattered reflection means that the intensity will be lowered. In the back propagation, the intensity will be lowered. So if you can calibrate these things, then you can calibrate it in terms of the deflection vis-a-vis the reduction in the AE count, acoustic emission count. So this is the technique which people are using for detection of the growth of any irregularities. Anyway, you can also use other techniques like eddy current crack detection technique, but that's a relatively static. Even the laser you can use, or ordinary light you can use, everything. Whenever some discontinuity is there, there's a fundamental law of optics. Whenever some discontinuity is there, there will ought to be some diffuse scattering. So that means the return wave will always be of lower intensity. So you can really get this. So this is a philosophy, and I will be moving a little faster now. Now, whenever any particular component fails, Then the cracks, when the crack is, it's not very important for us to know how many cracks are there in my design component. It's important that how many cracks are there whose sizes are above a threshold size. So what is that threshold size? Who will tell you? I will tell you that the Paris law will ultimately say. Right now I am going to describe it. Now, the crack size ultimately determines the threshold. Because once the crack reaches or exceeds the threshold size, then the crack propagation becomes catastrophic. It will not obey any rule, and it will the component gets fractured. So that is the point that we have to find out the threshold crack. What is the time required for the crack to activate that threshold size? So this is a task. So how do we do it? I've already discussed this point. Now, normally a failure is obtained when that is dependent on the threshold of a failure is obtained by the fracture mechanics. So the first formula is K, the linear elastic fracture mechanics. So that is a fracture toughness K. If type 1 loading is there, then K1, and the type 1 loading is there. If it is a threshold crack, then this is a threshold value of K, then it is K1C. So this K1C is a linear elastic fracture toughness. What does it physically signify? It signifies the amount of energy which the material can absorb prior to the failure. So that is what is the important part. Now, that's one thing. So you have to calculate that thing. So this K you have to calculate. अरे वो कहाँ गया? ये जो ये दिखाना होता है, वगैरह विशाल पॉइंटर लेजर पॉइंटर यही सकेगा होगा नहीं, वो एक साथ आता है। बताओ कैसे आता है, जल्दी बताओ, इस पॉइंटर को बताओ, जाओ तुम जाओ कैसे होता है। Good, very good. You see that this is the linear elastic fracture toughness. Sigma is the applied stress, so which you are applying from outside. And the pi and this A is the crack. When the crack length is 2A, normally we say that A is a half crack. So this is the formula, and this is the correction factor. So forget about it, that's a constant. But it's not possible that everything is absolutely linear elastic, because the material will be highly brittle. So normally any engineering material are elastic plastic. So very small amount of plastic deformation is there. And for that, the J integral is a method. Why I'm not going into that, but this is the formula of J integral, which we can do. And this is expressed in the work done, that is the energy absorbed, and there is a stress-strain relationship. So epsilon is a stress and the sigma is a stress and epsilon is a two strain. So here you see that sigma ij, whenever I write ij, you might be exposed to the tensor. So see, the stress is a tensor, strain is a tensor. So of rank 2, if you do not know, I will not bother you, but you should know. So the tensor, the sigma ij is a tensor, a stress tensor, and this is a strain tensor. But I and j values, the 9 components are there to specify stress at a point as well to strain at a point. Ni is a normal vector components, u is a displacement vector. So this is what is there. And then ultimately it becomes a j is equal to k square. The j is related to k. That means the k is a stress intensity factor. So at the crack tip, how much stress is generated, its intensity is determined by k. And then the k is again determined by the amount of energy absorbed. So this k square divided by E divided by 1 minus nu square. Nu you know what's the ratio, E also you know elastic constant. So this is how the J is made related to the stress intensity. Why do I say? Because I will be simulating this thing. Now, this is a famous thing that when exactly the crack will start propagating catastrophically, so that the failure becomes immediate. So that is the rate of crack propagation, DA. When the fatigue cycling loading is there, the number of cycles depending on the length, the crack growth with respect to the number of stress cycles is given by some constant into delta K. That is the initial cycle was K1, next cycle K2, so K2 minus K1 raised to the power A. M is an exponential constant. If you take the log, you can treat it like this, and then you can get this one. Ultimately, you can also replace this one, that from here you can write this thing, and then you can convert it. So dA dN. So you can write that dN dA, and this is how you can write the entire thing. So it is a simple transposing of equations to your convenient form. Then ultimately I'll be getting this one. Why? Because I now want to integrate that N is an acoustic emission count. So I am now acoustic emission count vis-a-vis the crack growth also follows a similar relationship. So that is how I could relate this thing with some constants. The similar thing is there that each constant is different from the other constant, Paris loss constant. So if I combine these two, I have to generate the multiplication of two constants, so another constant is generated. So this is what I have done. So the D is a total constant out of that. So you have to know this thing, otherwise you will be confused. Now the thing is that the process is very simple. So once I get this form, then from here my job is to integrate. Once I integrate, then I have to calculate the integration constants. So how do I do that? When there is no crack, K is equal to K0 is equal to 0. When the acoustic emission will be N is equal to N0 into 0. So theoretical case. Now, if there is a crack, then delta K1 will be K1 into K0. K0 no. So naturally, this is delta K1. Similarly, delta K2 will be this. So this is how you can get the K2 minus K1, so delta Kn you can get. Once you get this thing, then you can integrate this thing, and then you get the integration is from I plus 1 to j, and you will be getting this thing, and then the entire constant is landed into this, and automatically some constant, some values are known, automatically it will be coming to this. So this P minus M, 2, all those things, they are the some kind of constants generated, and I simplified that such that a simplified equation is there. Okay. So once it is there, then I know that P minus M is 0.22. So ultimately I can replace this P minus M by this one, so I get this. So that means ultimately overall I get a constant G. So it's a mathematical juggleries which we did. So there we got some relationship. Finally, we got some relationship that this is the relationship. In terms of N, we got the relationship. So G is also known. So therefore, we got this. So this relationship we got. So delta N, the acoustic emission delta is this. So therefore, we now, what is our job? We have to simulate this thing. How do we do it? So for that, you have to define the global and local parameters. So a 2D rail section you do, and then CAD tools you use. Ultimately, you interface with COMSOL. In COMSOL, you can do that. And set the rail steel materials parameter. That will be asked. That will be asked by the mechanics toolbox of COMSOL. And then once you do that, then you will be getting the direction of crack propagation. Also, you have to prescribe, and then you have to build a mesh. The triangular base we used, and then at the crack tip, since everything is very fine, so finer base we design. So this is a finite element analysis. You can take any, but COMSOL will do it for you. No ANSYS business, nothing. And then A counts are obtained from the equation 22. The equation I told, the similar equation of Paris. So once we simulate it, then we find that these are the crack lengths against the stress intensity factors one like this, and the number of acoustic emissions. So that means this is related to this is related to this. Here, this is my illustration of crack. So this is a crack. So this is A, and this is the width of the rail track, and then this is a. So therefore, this is a cross-sectional view. With that, this is the actual railways. So it's that we did the work in Australia on this particular rail. So here, this is a plane strain situation. Why? It's a very long. So actually, strain along the third direction is zero, almost, because very small strain divided by the length, very long. So therefore, it's almost zero, negligible. So that is called a plane strain condition. So it's a plane strain fracture toughness you have to determine. So that's why you have to call in K as well as the J. So after doing that, what we can get is the stress intensity factor versus the stress. So as the stress is increasing, the stress intensity factor is increasing. That should be the linear. So here similar thing is there. So for the different crack length we have shown, I've just shown you that the similar relationship is there. Now whenever I go for the understanding of crack length versus stress intensity factor, I find a parabolic relation. If you recall the Paris law, that the K is equal to A into delta K raised to the power n into some constant, then it is a parabolic equation or some kind of multimodal equation, exponential equation. So it's like that, you see. But here you can find that there is a certain changes too. From here, you can very easily find what is the critical crack length, because here you find the crack is growing and it's a disruptive growth. So naturally, this is the point where you can get a better picture in here. You see that here, somewhere here, the crack growth rate is very, very large. So that is how you can get this. So crack length ultimately talks about stress intensity factor, and then this is the final picture of the simulation results. You see that it has now cracked and it has now deformed. Then it's a failure, track failure. And if we do not detect, there will be an accident and fatality. So this is possible. This is another way when in a laboratory eddy current we need, just to demonstrate that crack does not propagate so easily. It's not a single type 1 crack propagate. It changes its path. So it's a complicated situation. This is a demonstration. Now this is your eddy current output. You need not know unless you know it. This is our input. That we are now related to it. A count, because that's our thing. That physically we determine by non-destructive testing the A count. And a similar relationship is there against crack length. So here you find, from your own judgment, you can find that this is how, from here, it is rising very steep. So naturally, you can say, if you draw a tangent here, so you find that this is the point of contact, so it will be the typical crack length, the 12 point something. So there you can say that wherever you are measuring the crack length through acoustic, wherever this is 12.5, you can say, and you can also find out the time. You can interpolate it in terms of time. So this is the entire control algorithm flowchart. You see that we have simulated, or you have to simulate the stress intensity factor versus crack size. Then you have to have the experimental value of K1C. So once you have the experimental value of K1C, then you must know where exactly this K1C is going to be reached. So far before that, with a factor of safety, you will truncate your operation. You will say that corrective access is required. Because a factor of safety is right at that particular thing. You cannot say that stop it. You have to have that some kind of factor of safety. And then estimation of critical crack length, तो ये multiphysics से आएगा. And then simulation of AE count versus crack length, ये भी multiphysics से आएगा. Measurement system for the AE counts, the critical AE count, estimation of AE threshold. If AE threshold is yes, it will be like this. If yes, continue trend movement. If it is no, trend continue trend. If it is real-time railway crack measurement system, and you see, you feed it here. So here, decision making is there. What is the real-life crack and what is the requirement? Requirement is calculated on the basis of the fracture toughness K1C, which has been experimentally determined. So now we have to give judgment. If it is less than, that means the AE threshold is less than, if actual AE count is less than the AE threshold, then continue. If no, then alarm. Sound an alarm, and by that sounding of alarm, then you can have a control room away from the train. And from there, you can, in a remote control, the entire thing can be controlled, and you can, the catastrophic failure of railway tracks can be now controlled, and you can save the casualties, the railway casualties. So this is the control structures which we did. As I said that in Australia, the asset management was a very hot topic. So that time, I had the fortune of working on this, and then this is the thing. The corrective actions we can take, the reduce the speed or hold the operation, change the track, and then go. So this is how, this is the typical algorithm flow. Now, I must acknowledge this boy, the Upamanyu Banerjee from the National Institute of Technology, Trichy, who worked with me to model this thing that comes from multi-physics. So the entire sources are from his experiments, and then the modeling was done quite obviously through my input of this Paris law. Yes. I told you, look, console multi-physics. And the mechanics is the tool. 6 toolboxes were there at time, but right now the development has been there. So this is a typical platform for any of the mechanical engineers who want to give a check to the component. So ANSYS does not give you that kind of, you can finalize it, you can do it. With ANSYS, you can find out the fraction. What you cannot do is that this kind of simulation you have to do. In any case, you have to do it. So, as I said, that some kind of optical, I told that it is approximation. You can also take results, you can also take. But the theory is the basic physics. The practice is there. And the approximation is much clearer. Because whenever crack is given by an nanometer, crack go, then immediately the approximation is number of count 8 points. And from there you can do. And then you can try with ANSYS. I wrote object. I did it also because it's simpler to do. But you can. But provided you have the idea of Paris law, you have the idea, because one thing I can tell you, which will be helping you, why don't you do it? Which year you are in? MTech. Hey, Jires, this is your student? Huh? So you give him this project, he is interested. With the same models, same kind of models he will do in ANSYS. No, this is your project. I am giving it to you. Forget about Amar Patnaik Jires. You do it. Do you understand my point? So you can tell both of them, take my name that he has told me to do. And it will give you much credit, I see. This concept you can make use of anywhere. This was done in a railway track because that was a very important point. But any asset management, you can use this concept. And then you have to, of course, design the algorithm so that you are quite confident. Okay? Thank you very much. Oh, yeah. Genius, sir. Oh, Genius, sir. You told me to finish by 5. So I don't know. I did it. But जो कुछ बोल दीजिए सर ये तो good afternoon.
Thank you so much, sir, for you as usual enriching and thought-provoking session. It is always our pleasure to have you between us. We hope to collaborate multiple times in future so that learners could benefit from your experience. Once again, thank you so much, sir. So,
We are going to start already.
yes, sir.
Huh.
Dear participants, the feedback form already published on WhatsApp group, so you can fill the form. And during the filling the form, kindly ensure that you fill out the feedback form carefully, because the name you enter in the feedback form will appear on the certificate. So double check for spelling and accuracy before submission. Once you submit the feedback form, your certificate will be generated. Now we will move towards validation session that will be start within few minutes.